Okay, so we've looked at some of these simpler cases. Now let's look at some cases that are slightly more complex. So I call these double iteration cases. And so you can see here, instead of having x e to the x, we have x squared e to the x. So we have our choices just like before. We can, let u, we have to choose what u equals, and we have to choose what dv equals. Given the two choices, e to the x, it doesn't matter where I put it, but x squared definitely gets simpler if I put it in the u space. So I'll have e to the x down here. We have to differentiate x squared, and we'll end up getting du is equal to 2x dx, because du dx would be 2x. V would be the integral of dv. So if I integrate that, I will just have e to the x. Oh, and once again, I left off, that's e to the x dx, because I'm going to integrate both sides. So now we have our grid to work with. And the formula, let me write that out. The integral of u dv is equal to uv minus the integral of v du. Okay, so this is the integral of, let me switch back to blue. The integral of x squared e to the x dx, that's good, the original problem, equals uv, that's x squared e to the x, minus the integral of v du. Okay, so that's, looks like we have minus v du will be, 2x. I'll put the 2 in front, x e to the x dx. All right. Oh, well, now this looks like a problem we've done before. Let's actually break this out as a separate problem. So if we let this end up, let u equal x, dv equals e to the x. So we end up, well, it's not on the memory list. It's one of our integration by parts problems that we had done before. So du is just dx. And now v, whoops, once again, I left off the dx. V will be equal to, because u was the x and dv is everything else. So v must be e to the x. And therefore, the answer to this part must be that it is the integral of x e to the x dx must equal uv, so that's x e to the x, minus the integral of v du, so that's e to the x dx, and that simplifies to x e to the x minus e to the x. Right? Now remember, this answer was nested inside of the other answer. So to get the complete answer, going back up a step, we can say the integral of x squared e to the x dx is equal to x squared e to the x minus 2 times the answer we just got. So we can say 2 times x e to the x minus e to the x plus c. Let's see if anything simplifies. Doesn't look like it does, but we can at least distribute that -2. So I get x squared e to the x minus 2x e to the x minus 2 e to the x plus c. So there is the answer. We'll just, we will check this answer because it got a little bit longer, and we want to move on to another problem. Okay. We can do the same thing if I had the integral of x squared cosine x. We can use the same process, right? So we'll just have to do it twice, because the first time we take the derivative, x squared will become 2x, and the second time it will become a constant. So this will work out in 2 iterations. So I'm just going to go through that kind of quickly, and I'll talk it through as I go. So u is equal to x squared. dv is everything else, cosine x dx. du is 2x dx. V is the antiderivative of cosine, which is just sine of x. So my first iteration gives me that the integral of x squared cosine of x dx is equal to uv. So that's uv right here, x squared sine x minus the integral of v du. You can kind of see that it follows this little pattern, down and then up if you want to zig and zag. And then you have, so that gives me a 2 outside x sine x dx. Then I break this out as a separate problem. And I will let u equal x, dv equals sine x dx. So du must be dx. And v will be the integral of sine, which is negative cosine of x. All right, and then we zig and zag, and we can say that this part, the integral of x sine x dx, must be equal to zig, negative x cosine x, minus the integral of the zag. Oh, but that's a minus in there, so uv, so it becomes plus the integral of cosine x dx, right? And if I look at that, I can see that that's going to be negative x cosine x, and the antiderivative of cosine is sine, plus c. If I sub all of that back into the original problem, slide on up, I can say that the antiderivative of x squared cosine x dx is equal to x squared sine x minus twice all of this, negative x cosine x plus sine x. I'm just going to tack a new c, I'll call that one c1. So this will be my final constant right here with a little distribution, x squared sine x plus, did I get this right? Let's see, plus 2x cosine x minus 2 sine x plus c. So there we have the answer. Okay, so that's another one. That's kind of a longer one right there. Okay, so scroll through that. There's the answer to it, and there's the whole problem if you need to pause it to study it at all. And let me move on to a third case. Okay. These two cases are a little bit different. In fact, this case looks like it'll be the same, but it isn't. Okay. This one actually doesn't require multiple iterations because as we learned in this problem, we can't put ln x here. So this is not following the same pattern. We don't know how to integrate it. Well, we actually do now, but we don't want to use that. We want to always put the natural log up with as u because it gets much simpler once we take the derivative. So going back to this, it turns out this, while it looks like the first two, really isn't, because du is 1 over x dx, right? And v is x cubed over 3. And interesting things will happen, okay? So if I do my zigzag, I'm not going to write out the whole formula anymore. I'll do my zigzag. So zig, so my zig gives me x cubed over 3 ln of x minus the zag. So the zag is the straight up again, v du. So if I zig and zag, I now have x cubed over 3 times 1 over x dx. And you can see how the integral simplifies. I'll bring the 1/3 out. We're left with an x squared. All right. And then we'll have a dx. And we know how to integrate that. So x cubed over 3 ln of x minus 1/3. And then the antiderivative is x cubed over 3 again, plus a c. And obviously we want to simplify that last fraction down, so we have x cubed over 3, or 1/3 x cubed, ln of x minus x cubed over 9 plus c. So that was not an iterative process. Notice we only had to do it once because it looked like it was going to be iterative because of the x squared. But when you have ln x, you always make that u, all right? Just because we don't know how to get dv for it, or if we now know how to get dv, we did learn that in the last video, but it's a complicated thing. So we would much rather have ln of x being the u, and so we don't have to do an iterative process. So x squared got worse, but ln of x, when we took its derivative, became much better. So the combination ended up giving us something here that could become straight up power function, which is on the memory list. One final problem. So study that if you need to. Pause the video, make sure you understand how that worked. Now we're going to do one more that is iterative in a new kind of way. So this is a pretty classic problem. I am going to do e to the x sine x. A couple of others that are iterative, I'll put these on the side, that are going to behave in almost the same way, and that's sine squared x dx, because that would really be a sine times a sine, or cosine squared of x dx. These are two others that follow this same process, but I'm going to show this with e to the x sine x. So if I look at this, it's a little bit baffling. Let u equal dv equals, all right? When I put those two things together, it's not obvious which one I want to put where, except I sort of prefer taking the derivative of the sine of x because it will be a nice derivative. So I'm going to let dv equal e to the x dx. So when I look at this, I end up with du must be cosine x dx, and v must equal e to the x. Okay, so let's try to figure out what happens here. We will start by using the formula, the integral of u dv, the original problem, must equal zig, so that's uv e to the x sine x. We put the e to the x out in front. We always want our trig functions at the end, so their argument is very clear, minus the integral of v du, so that's my zag. That's e to the x cosine x dx. All right. It looks like we went nowhere, all right? But we did actually go somewhere. It's not obvious yet. But let's bring this out as a separate problem. So if I start this as a separate problem, I can let u and dv, this time I think I'd rather integrate cosine of x, and I would rather, so I'll differentiate e to the x. E to the x doesn't matter which way it goes. But the antiderivative of cosine is just a sine, so I would rather have that. And du must be e to the x dx. So breaking out this part of the problem, the integral of e to the x cosine x dx equals zig e to the x sine x minus zag. All right, so e to the x sine x dx. Now it looks like we've gone exactly back to the beginning, right? Now this is a good thing though. This is exactly what we want, because you'll notice that we have it as a negative on this side of the equation. So, oh, let's see, did I get a sign wrong in here? Let's see, I need that to be, so we're going to subtract it. So let's see what happens here. think I have an error in here somewhere, and I'm going to have to find it. Let me pause. Oops, I'm sorry about that. I thought I had paused, but I hadn't. We got a little blank space in there. I did figure out what was wrong. The problem is I can't do what I did here. I just undid what I had done previously. Okay, so once I need to get rid of this. In the first step, let me go back when I had decided that u would be sine x. If I let dv equal cosine x in the second step, I'm going to actually get back to a point where 0 equals 0, which is very true, but not helpful. So what I needed to do was say let u equal cosine x, and dv is equal to e to the x dx again. All right. And so while I would prefer integrating cosine x, I have to differentiate it to do that. I have to do the same thing twice. So v is equal, and that'll have a dx. V will equal e to the x. And so now I can do my crisscross. And this will equal, so the integral of e to the x cosine x dx will equal e to the x cosine x minus the cross, which becomes plus e to the x, minus the integral of that, plus e to the x sine x dx. All right. Now, when I put everything back in, we're going to see something very nice happen. We're going to get a doubling effect. So over here on the left, we had e to the x. It looks like we just ran in a circle, but we didn't. Okay, it looks like at the end of all of this, I ended up with the original integral here. Okay, but the dx. Now let's distribute that negative sign. So we can say the integral of e to the x, and I'm copying this one purpose. Whoops, I left the x out there, is equal to e to the x sine x minus e to the x cosine x, okay, minus the integral of e to the x sine x dx. Now here's the really nice thing, okay? While these two are the same, notice the subtraction sign. That means to get this, to get it to go away on the right-hand side, I should add it. And that means that twice the integral of e to the x sine x dx must equal e to the x times sine x minus e to the x times cosine x. Wow, okay, so we are almost to the finish line. All I have to do is half both sides. So it's going to be a 1/2, and I'll factor, that's a times there. Both terms have an e to the x. So I'll factor the e to the x and divide by 2. So you get e to the x over 2, or half e to the x times sine x minus cosine x as the answer. Okay, so that came out to be something that we could do by an iterative process. All right, so 3 of the 4 examples that I gave you were iterative. One looked like it would be iterative, but really wasn't. The first 2 are the important ones. I think you're going to see ones like that in the homework.